So far, we have seen what are Cauchy-Riemann equations, and using those Cauchy-Riemann equations, we derived an equivalent criteria for checking the differentiability of a function. So these are really useful equations for checking differentiability of a function. Now, let's revise what we have done so far. So we have the result which says that if a function with components u of xy plus iota v of xy is given and the function is defined in some neighborhood of the point z0, and if the partial derivatives ux, vy, uy, vx exist everywhere in the neighborhood, and if the partial derivatives are continuous and satisfy the Cauchy-Riemann equations. So if all these conditions are satisfied, then we say that the function is differentiable at that point z0, and we can calculate the derivative using either of the equations. Now, this result or this theorem, which is equivalent criteria for the differentiability, is basically for the function when it is given in the Cartesian form. So over here we can see that these x or y, so these x and y's are basically the Cartesian coordinates of the complex number. Now we have seen that there are many forms in which we can write down a complex number. So it's a Cartesian form, or it's a polar form, etc., etc. Now the question is, can we find an equivalent criteria for differentiability in polar coordinates? So this is going to be our topic of discussion in this session. So the answer is, of course, yes. We can derive an equivalent criteria for the differentiability, for checking the differentiability in polar coordinates of a complex valued function. Now, what do we know? So we know a relationship between Cartesian coordinates and the polar coordinates, which are r and theta. So x is equal to r cosine theta and y is equal to r sine theta. So over here, so if we are given a complex number z with the Cartesian coordinates x and y, so this means that this direction is basically x and this direction or this length is basically y. And using these two lengths, we can find the length of the diagonal. So we can find this r and we can also find this theta using these expressions. So there is a relation between the Cartesian coordinates and the polar coordinates of a complex number. So intuition says that we should be able to find or convert the Cauchy-Riemann equations in Cartesian coordinates into some expression in polar coordinates, and those expressions are going to be our Cauchy-Riemann equations in polar coordinates. So this is our aim. So we want to use these relations between polar and Cartesian coordinates to derive Cauchy-Riemann equations in polar coordinates. So what are Cauchy-Riemann equations? So in, of course, Cartesian coordinates, so ux is equal to vy and uy is equal to minus vx. Now observe that these equations relate partial derivatives with respect to the Cartesian coordinates x and y. So what do we want to do? So we want to write down these partial derivatives in terms of the partial derivatives with respect to the polar coordinates. And what are polar coordinates? R and theta. So we want to write down ux, uy, vx, vy in terms of ur, u theta, vr and v theta. So how do we do that? So for that, we must use chain rule from multivariable calculus, because u is a function of two variables x and y are further functions of two variables r and theta. Now let's see what is chain rule. So if we are given a function u which is a function of two variables x and y, and if x is further function of two variables r and theta and y is further functions of two variables r and theta, then we can calculate the change in u with respect to either of the variables r and theta using chain rule. Now let's see what is the picture. So u is a function of two variables x and y, and these x and y are further functions of r and theta. Okay, so now if we want to calculate, for example, what is partial u by partial r. So over here we can see that u is a function of x and y are further functions of r and theta. So u is a function of r and theta. So we can talk about what is rate of change of u with respect to r. So over here we can see that so there are two r's at the bottom or in this tree. So we want to write down the contribution in the change of u with respect to each of these branch. Okay, so there are two branches. So this is the first branch and this is the second branch. So we want to write down the contribution for the change in u for each of this branch. So for the first branch, let's write down what will be the rate of change. So this first branch is partial u by partial x. Okay, so we move from u to x, and then rate of change multiplied with the rate of change of x. So partial x by partial r. Okay, so now what about the second branch? So plus the second branch is so partial u by partial y. Okay, so the rate of change of u with respect to y multiplied by the rate of change of y with respect to r. So that's how we calculate, or we use chain rule to calculate what is partial u by partial r. Okay, so similarly we can calculate what is partial u by partial theta. Okay, so in this case, so we have the following tree: u as a function of x and y, x and y are further functions of r and theta. So over here we have two branches. So to approach this theta, so this is the first branch and this is second branch. So with respect to the first branch, what do we write? So we are calculating partial u by partial theta. Now in the first branch we have partial u by partial x, and then we have partial x by partial theta. And for the second branch, let's see what will be the output. So for the second branch, plus so partial u by partial y and multiplied with partial y by partial theta. So this is the chain rule when we are calculating the rate of change of u with respect to r and theta. Now we have the same situation over here. Okay, so we want to calculate what is partial u by partial r, and over here x in particular, x is r cos theta and y is r sin theta. Okay, so by using chain rule, this is equal to partial u by partial x multiplied by partial x by partial r plus partial u by partial y multiplied with partial y by partial r. So in this case we can calculate what is partial x by partial r. So we can see that in this case partial x by partial r is going to be equal to cosine theta. And okay, and what else do we need? So we need partial y by partial r. So what is partial y by partial r? So this is equal to sine theta. So this implies that basically u r, or the partial derivative of u with respect to r, it is in fact equal to ux multiplied by cosine theta plus, okay, so uy multiplied by sine theta. So this is the relation between the partial derivative of u with respect to the polar coordinate r and the partial derivatives of u with respect to the Cartesian coordinates x and y. So we have the following result. So what is ur? We have calculated using a chain rule. So this is equal to the partial derivative of u with respect to x cosine theta plus uy, which is the partial derivative of u with respect to y sine theta. And on the same lines we can calculate u theta, which is the partial derivative of u with respect to theta. So I'm leaving this as an exercise, but we can easily see that this is equal to minus ux r sine theta plus uy r cosine theta. And on the same lines we can calculate what is vr. So basically vr is going to be equal to vx cosine theta plus vy sine theta. Let me remind you, we are using the chain rule that we have discussed earlier to calculate these partial derivatives. And similarly we can calculate v theta, so the partial derivative of v with respect to theta. So this is equal to minus vx or sine theta plus vy or cosine theta. Now let's see if we can find a relationship between ur V are V theta and U theta V are V theta. Now observe that if we start from U theta, and U theta is basically equal to minus Ux r sine theta plus Uy r cosine theta. And if we take minus r common, so we get Ux sine theta minus Uy cosine theta. Okay. Now we know that if Ux, okay, so if Cauchy-Riemann equations are satisfied, then this Ux is equal to Vy. Okay, so this becomes minus r. So this Ux is basically equal to Vy sine theta. And similarly, this Uy is equal to minus Vx. So minus and minus plus, so this becomes plus Vx cosine theta. Now let's see if we can find this thing over here. So this is basically Vr. So Vy sine theta and Vx cosine theta. So we can say that this is in fact equal to minus r Vr. So using Cauchy-Riemann equations and using these partial derivatives, which we have derived by using chain rule, we can easily find the following condition, that U theta is equal to minus r Vr. And using the same process, we can also find the following relation, which is r Ur is equal to V theta. So these conditions are basically equivalent to the Cauchy-Riemann equation in Cartesian coordinates, which is Ux is equal to Vy and Uy is equal to minus Vx. So in other words, if these polar form of Cauchy-Riemann equations are satisfied, then this implies the Cartesian form of Cauchy-Riemann equations are satisfied. And if these Cauchy-Riemann equations in Cartesian coordinates are satisfied, then they imply that the Cauchy-Riemann equations in these polar coordinates are satisfied. So we have derived what are Cauchy-Riemann equations in polar coordinates. Now let's try to convert our necessary and sufficient condition for checking the differentiability into polar coordinates. Okay, so over here the function is given in polar coordinates. So the component function, so the real part is function of r and theta, the imaginary part is a function of r and theta, and we want to check, or we want to write down a result, a necessary and sufficient condition, which will check the differentiability at a complex number, and the complex number is given in terms of the polar coordinates r naught e raised to power iota theta naught. So the first condition is the function should be defined in some neighborhood, and the first condition is the first order partial derivatives of the functions u and v with respect to r and theta exist everywhere in the neighborhood, and we are moving very parallel to the Cartesian case. Okay, so over there we imposed the condition that ux, uy, vx, vy exist in some neighborhood of the point z naught, which was equal to x naught plus iota y naught. So it is exactly the same condition. And the second condition is the Cauchy-Riemann equations for polar coordinates are satisfied, and we have seen that these equations are equivalent to the Cauchy-Riemann equations in Cartesian coordinates. Okay, so if these conditions are satisfied, then the function is differentiable, and we can actually calculate the derivative of the function at point r naught e raised to power iota theta naught. So let's try to solve some example. We are given this function, which is basically the principal cube root function. So we know that if we calculate cube root of a complex number, then we get 3 answers. But one of them is basically correspond to when we just divide the principal argument or the argument of the complex number with just 3. Okay, and the other 2 are basically derived using the fact that this theta is equal to theta plus 2k pi. So this is the principal cube root function where we are just dividing the principal argument with 3. Okay, and other 2 roots can also be defined, but this is the principal cube root function. So what do we want to do? Okay, so first of all we restrict the domain. So over here we can see that since polar coordinates of a complex number 0, 0 are not defined, so that's why we impose the condition that r is greater than 0, and the variation of theta is basically minus pi to pi. So we want to show that the function is differentiable and the derivative of the function is given in the following way for every point in the domain. So now we want to use the necessary and sufficient criteria which we just derived, and so the first condition is, so the function should be defined in some neighborhood of the point, and in this case, yes, it is defined. So the second condition is the first order partial derivatives of the functions u and v with respect to r and theta must exist everywhere in that neighborhood. So let's see what is u in this case. So u of r theta in this case is equal to r raised to power 1 by 3 cosine theta by 3. Okay, and similarly we can see that v of r theta is basically equal to r raised to power 1 by 3 sine theta by 3. Now let's see what is ur, or the partial derivative of u with respect to this polar coordinate r. So this becomes basically 1 by 3 r raised to power minus 2 by 3, and there will be no change in cosine theta by 3. Similarly, we can calculate what is u theta. So u theta is equal to basically minus 1 by 3 r raised to power 1 by 3, because there will be no change in r and we are only taking the derivative of cosine theta by 3. So this becomes sine theta by 3, and theta by 3 has derivative 1 by 3, and the derivative of cosine is minus sine. Now let's calculate what is VR, the partial derivative of V with respect to R. So this is equal to 1 by 3 R raised to power minus 2 by 3, and there will be no change in sine theta by 3. And similarly we can calculate what is V theta. So this is basically equal to 1 by 3 R raised to power 1 by 3 cosine theta by 3. When we are calculating V theta, so we are just taking the derivative of sine theta by 3. There is no change in R raised to power 1 by 3. So the partial derivative exists. So basically they exist for every point in the domain. So the second condition is satisfied. So the third condition is they must satisfy the Cauchy-Riemann equations. Now let's see if they satisfy the Cauchy-Riemann equation. So the first equation is, we must have, when we multiply r with ur, then we must get v theta. So we have calculated what is ur. So ur is basically equal to 1 by 3 r raised to power minus 2 by 3 cosine theta. And we also calculated what is v theta. So v theta is basically equal to 1 by 3 r raised to power 1 by 3 cosine theta by 3. Now let's see if we start with the v theta. So v theta is equal to 1 by 3 r raised to power 1 by 3 cosine theta by 3. So is this equal to r multiplied by ur? R multiplied by, so what is ur? So 1 by 3 r raised to power minus 2 by 3 cosine theta by 3. Okay, so there should be cosine theta by 3. Okay, so we can simplify this thing, and we have 1 by 3. So r raised to power 1 multiplied with r raised to power minus 2 by 3 becomes r raised to power 1 by 3 cosine theta by 3. So this first Cauchy-Riemann equation is satisfied. And similarly we can see that, so similarly u theta is equal to minus r, Vr is satisfied. So the third condition is also satisfied. So we can say that according to our criteria, the necessary and sufficient criteria for checking the differentiability, this function is differentiable. And if we actually want to calculate its derivative, then we use this condition. Okay, so what is ur in this case? So ur is basically equal to 1 by 3 r raised to power minus 2 by 3 cosine theta by 3, and Vr is basically equal to 1 by 3 r raised to power minus 2 by 3 sine theta by 3. So basically f prime of z naught, and z naught is given in terms of the polar coordinates. So this becomes, okay, so e raised to power minus iota, and we have theta naught because we are calculating it at point r naught e raised to power iota theta naught. So this becomes 1 by 3 r naught minus 2 by 3 cosine theta naught by 3 plus iota 1 by 3 r e raised to power minus 2 by 3. So this is r naught and sine theta naught by 3. So this is the value of the derivative at point r naught e raised to power iota theta naught. Now if we want to convert the value of the derivative in terms of Cartesian coordinates, then we start with this expression, which is the derivative. If we simplify this thing, so simplify in the way that r raised to power minus 2 by 3 and r raised to power minus 2 by 3 and 1 by 3, 1 by 3, so they are common, and what we are left with cosine theta by 3 plus iota sine theta by 3. Okay, so which is basically e raised to power iota theta by 3, and if we multiply e raised to power iota theta with e raised to power iota theta by 3, so we get the following expression. So there will be theta, and simplifying it further, because z raised to power 2 by 3 is basically equal to r raised to power 2 by 3 and e raised to power iota 2 by 3 theta. So using this thing, we can easily say that, so this is the derivative of this function f of z. So f of z is basically z raised to power, okay, so in fact f of z is z raised to power 1 by 3. Okay, and the derivative of this is basically equal to 1 by 3 z raised to power 2 by 3, which we have calculated using the polar coordinate version of Cauchy-Riemann equations. So in this discussion, we have derived the polar version of the Cauchy-Riemann equations and a necessary and sufficient criteria for checking the differentiability in polar coordinates. So once again, these criteria are going to be very useful for our further discussion for checking the differentiability of a complex valued function.